So we're going to talk about exception-safe code, and I want to start by saying that there's a website. It has a bibliography, the stuff that I researched in order to put this stuff together. It's a little bit out of date. There's been some more interesting stuff that's come out since then, and I haven't always added that to the bibliography. But the basic stuff that I'm going to tell you has been true for a very, very long time. It hasn't been updated for 11, so there's that stuff too. There's a video there of this talk, but in a month we'll have the video of this talk, which is probably going to be better, and certainly going to be a better quality video. So we'll update that at the time. And it's also a place where you can send me any comments that you have about the talk. Of course, you're in person, so you can also just let me know. You can reach me at that address. You can follow me on Twitter. If you want to work for a company that takes C++ seriously, as I say, send me your resume in mind. I want to dedicate this talk to a great teacher of exception-safe coding. Yoda is our, there you go. So many people know that, a galaxy far, far away, a long time ago, he was teaching Jedi Knights how to use the Force. But more recently, in our galaxy, he's teaching C++ programmers how to use exceptions. And so he's the one that we're going to model. So I have a promise that I'm going to make that we're going to get to by the end of the third session. And that promise is that if you follow the guidelines that I'm going to give you, you internalize what I'm saying and follow those guidelines, the code that you write will be easier to read. And by that, I mean it'll be easier to understand and easier to maintain. And it'll be easier to write to begin with. I believe that what I'm telling you, I am giving you some discipline. You have to follow some constraints, but in general, you'll find it's actually easier to write code this way. And I want to say there's no time penalty. This is a little bit of an interesting question when you get into that because there's, in every case. But I will say at this point, no time penalty, and we'll dig into that a little bit more. And then I'll also say it's 100% robust in the face of lower level exceptions. Obviously, you can still write code that's not 100% robust. But in the face of exceptions, if you follow the guidelines that I'm going to lay out, these are what will happen. And so I want you to hold me to this. We'll come back to this at the end and see if we got there. So the other thing I want to say is that this course is kind of evolving. When I started, C++ 11 wasn't out yet. Now it's out. How many of you, let's do it this way, how many of you, although you'd like to, you really aren't using C++ in your professional life yet? Okay, so that's not too many. How many of you are totally C++ 11, old style C++ in the rearview mirror? How many of you are totally 11? All right, so the rest of you have got like some projects that are some of each, or maybe some platforms. Or is that what we're looking at? That's kind of where I expect you to be. So you'll see these little green bubbles at the top, right? If none are there, you can assume that whatever we're talking about is just applicable to both. If you see the 2003 bubble, then that means it's really applicable to 2003. If you see the 2011, then that means that it's applicable specifically only to 2011. If you see both bubbles, it usually means the slide, you have to think about the different things in different parts, right? Most of it, there's no bubbles, so, and that's the thing, is C++ 11 in a sense is a whole new language, but in another sense, fundamentally it's the same language. If it was completely different, then I couldn't do this. Most of what I'm telling you works for both, and so we can have a single topic that covers both. So here's what we're going to do. We're going to start talking about, and I will say, this is intended to be a single presentation, so I'm not sure exactly where we're going to go. Our mic's not on. Okay. All right, let's start over. No. Sorry about that. I apologize to the. Yeah, there's an exception. The first thing we're going to do, as I was going to say, is this is designed as one exactly presentation. I'm not sure exactly where we're going to break. If you have to go to another session because there's a really interesting session somewhere else, feel free to do that. You can catch the rest in the video. But I'm just going to more or less assume that it's us all the way through, and we'll do it that way. Right? So the first thing I'm going to do is I'm going to talk about the problem, because it's not necessarily obvious what problem we're trying to solve. But if we talk about the problem first, then I think we have a better path on the solution to that problem. And then we're going to talk a little bit about solutions that don't require exceptions. Because the problem that we're going to talk about is universal. It's just all through computing we have this problem. And so obviously, some languages don't have exceptions at all, like C. So obviously the problem can be solved without exceptions. So we'll talk about some approaches that we can make that don't use exceptions to solve the problem. But then we're going to talk about when you do use exceptions, some of the issues you run into. Then we're going to talk about some blind alleys. Don't try to do this. And then we're going to talk about the guidelines. So when we finally get to the guidelines, that's kind of the really important stuff, but we need the background stuff to get there. And then we're going to talk about some implementation techniques. These are things that make writing exception-safe code easier in some ways. And some of the really important stuff is there. So you want to be there for that, or watch it on the video, however it works. So what's the problem? What is it that we're trying to solve with exceptions? And what I would say the problem is it's the separation of error detection from error handling. And what do I mean by that? What I mean is that when you write code, we're looking at application logic and low-level implementation. And when I say application logic, I may not be talking about an application. I mean, it could be an iPhone app, or it could be a desktop app, or it could be a driver, or it could be CGI for a website, or something like that. But in all these things, even if it's not an app, there is application logic. There's some high-level logic that knows what the heck we're trying to do. And then there's low-level implementation that actually has to do it. And here's the challenge that we have, is that very often there are layers of code in between there, right? Well, why does this present a problem? Well, the reason it presents a problem is, where are we going to see errors occurring? Now, we could have logic errors anywhere, but if we're talking about physical errors, runtime errors that have to do with, trying to open a file that we don't have permissions for, trying to write to a file when we're out of space, trying to get memory when we're out of space or out of memory. All those things are going to be detected at this level, right? And then how are we going to handle these errors? And by handle, what I'm saying is somehow we have to tell the user that this error happened. Now, maybe the right thing to do this is to put up a dialog and say, this error happened. Maybe the right thing to do is we've got some server process and we just want to log that it happened. Or maybe we want to send back an HTTP error saying, 401 or whatever. What room are we in? 406. What is 406? I don't know what that is. Anyway, it turns out that you do not want to have your low-level implementation to know that, right? If I'm writing a low-level implementation, I want somebody, read this file and look for this or something like that. I don't want to tie that to, you can only run this particular function on an iPhone because I've tied in the error message from the iPhone, right? I don't want that. I want the low-level implementation to just do its job, and if there is an error, to somehow say something way up here to the top and say, you have to do the error, because the application logic knows. The application logic knows I'm a CGI, I'm a web handler, or I am an app, or I am whatever, I am a driver. It knows how to record errors. And so this is the challenge we have, that we have this separation between the low-level implementation that detects the errors and the high-level implementation, or the application logic that can handle that. So let's talk about a couple of ways of approaching this if we don't use exceptions. And as I say, there are some languages that don't even have exceptions. And there are certainly people, even in C++, in other languages that do have exceptions, that are trying to solve the problem without using exceptions for one reason or another. A lot of times it's because of fear, uncertainty, and doubt, but sometimes there's good reasons why we don't want to use exceptions. Don't ever tell Chandler I said that. Anyway, so there's a couple of things, and one way is what I call error flagging, and the other is return code. So let's talk about error flagging. So error flagging is, I just made this term up, but what it means is that there's some way that we set a flag somewhere that says, hey, look, there's been a problem. And the nice thing about this is that your low-level code doesn't need to know what you're going to do about that problem. It just says, I found a problem. I couldn't open the file, or whatever the problem was. And it sets a flag. And then it just returns, says, OK, I discovered an error. I did what I needed to do, and I'm on my way. And then the application logic checks and says, oh, look, there was an error. And I know that I respond to that error by putting up a dialog or writing a log file or whatever I do, right? So one example of this is a get error function that might be called to find out if error no is set or something like that. So here's an example of this. This is from a POSIX function, and it's actually the example of how you would do this. You set error no, clear it, then you call get priority, and then you want to check error no, and if error no is set, then you set the handle. Okay? This is not the most common approach. The most common approach, of course, is what we're going to talk about later, which is return codes. But this is an approach that is an alternative. So what are the problems? Well, one of the problems is that we can ignore errors. In fact, it's pretty easy to do that. By default, you're going to ignore it. You have to go out of your way to say, okay, I need to check if there was an error here, right? And so particularly when we start to do code maintenance and things like that, it's just really, really easy to write code that will ignore errors. The other thing is that you may have some ambiguity about what call failed. So you may have, if you forget to check errors after every single function call, or if you have a more complicated expression that maybe have a couple different function calls, it may not be obvious what tried to set the error. And so that may be important. It may not be. And then this code is kind of tedious, both to write it when you're writing, I got to check error again, I got to check error. And then I got to think about what am I going to do if there's an error. And then when I'm reading the code, I see, here's the logic, checking errors, of course. Here's some more logic and more error checking. So both reading and writing is kind of not fun. So let's talk about return codes. The return code is simply, everybody's seen an API with return codes, right? I don't have to explain that. You return some value that says some error happened, right? And then you have the responsibility as a caller, you have a responsibility to check that, and then you need to relay that up the chain, or maybe you have a different way of reporting an error, or maybe you know how to handle an error locally or something like that. So what are the problems with this? Well, it turns out the problems with return codes are really similar to the problems with the flagging, right? There is that by default, if you don't go out of your way to do something, the errors are just ignored. And here's a situation where if one function isn't returning error codes properly, you've broken the chain. You can't get back into it later. Some function that's properly written can't recover from the fact that it called a function that didn't properly return the error code. And again, tedious to read and write, because again, you have all this code that's explicitly checking for errors and doing something about it and propagating errors up, right? So it turns out that exceptions very nicely handles both of these situations. But, exceptions has its own issue. So let's talk a little bit about the dark side of exceptions. And what Yoda says is, broken error handling leads to bad states lead to bugs lead to suffering. So it turns out that that writing, did I get this right? Yeah. Writing code, writing exception-safe code using exceptions is tricky code, and we can have situations. So I'm going to show you this little snippet of code. Anybody want to step up and volunteer and tell me what this is doing? What's this doing? Okay, this is an assignment operator, right? And what are we doing? We're doing a destroy in place, and then we're going to do a construct in place. Do you know who wrote this code? First of all, do you write code like this? Okay, everybody disavows this code. I'm going to tell you who wrote the code. One of my idols wrote this code. This is the original implementation for the vector class written by Alex Stepan. He wrote this code. Of course, he will also tell you that the reason he wrote this code, he was at Bell Labs when he wrote this code, and he went to the C++ experts there and said, how do I write an assignment operator? And he said, this is how you do it. This is how you do it. Why? Well, because look how we're reusing code, right? When you write an object that, however you destroy the object, you write that once, you put it in the destructor. And whatever you have to do to create the object, you write it once and you put it in the constructor. I guess I should say what's actually going on here, right? We are manually calling the destructor, so we're doing a destroy in place, and then we're calling placement new, we're saying create a new, we're calling constructor here, create a new one in this place. So no allocation happens, we create it in place, right? And Alex, you know, he was writing the STL, and he was showing it to other experts in C++ and saying, here's how I think we should write container classes. This is using, this is the cutting edge stuff. And 6 years went by before somebody looked at that, and what did they say? No. What's this class about? They said it's not exception safe. Why is it not exception safe? Right. It's possible that this constructor could throw, and if it does throw, what's the state of the object? It's undefined behavior as soon as you try to use it. If you never actually used it after this, you'd actually be okay. But of course, you've got an object, and somebody's going to use it, and at least they're going to try to destroy it. Yeah.
It's undefined behavior even if you don't use it. The second destruction will be undefined behavior.
Yes, when this is eventually destroyed. Yes, when its destructor is eventually called. Yes. It is possible that it could be an alloc object, and then we just leak it. But it's not going to be, you're not going to have a good day, right? All right, so I don't show this to in any way denigrate Alex. As I said, he points out he didn't actually write the code, right? Somebody else did. The reason I show this is not to make fun of the early C++ programmers. It's to say, look how far we've come, right? The language rules that were in place here are still in place up until C++ 11, and frankly, none of those rules have actually changed. But everybody in this room says, I wouldn't write code like this. Now think about that. This is how the experts wrote code way back in the early days, and yet everybody in this room knows, no, we're not doing that. That's not acceptable. That's not exception safe, right? So my point is, we've learned a lot about exception safe coding as an industry. And the things that I'm going to tell you today, I wish I was the genius that came up with it, but that's not what happened. What happened is that we've, as an industry, figured out these kinds of things, how to write exception safe code. So one of the things I want to say, and I will say this because this is kind of my personal experience. When I first started learning C++, you guys probably can't see it in this light, but there's a little bit of gray hair here, and I've been doing this for a little while. But when I first started using C++, somebody said to me, oh, that C++ stuff, yeah, that's pretty good stuff. This was an experienced person. He said, it's pretty good stuff, but you want to stay away from two things. You want to stay away from templates, and you want to stay away from exceptions. Because those were the scary things. And there was actually some merit to what he's saying. Is part of it is people didn't understand them very well, but part of it is that they weren't always well implemented. And so I hope these things are behind us, right? We have a better understanding about how the language is supposed to behave, and we're also in a better situation about understanding how we should write code, right? So I hope this is behind us. But what are we looking at today? What is it that people are afraid of now? Well, I think one of the biggest problems is code path disruption, right? Now, there's every possible language out there in the world, but I shouldn't say almost all, but the vast majority of languages have one thing in common, which is that we execute a line of code, then we go to the next line and we execute that line, and then that is so innately expected of everyone that's how we read, that's how, this thing, and then this thing, and then this thing. And we don't, at the end of every line of code we write, we don't, in any language that I know of, say, okay, now go to the next line and execute it, right? Because that's kind of the default. We just expect that to happen. And it is so expected that if I was writing in a language where suddenly that's not going to happen, I've got line of code, line of code, line of code, but when it executes, it does line of code, and then it goes over here, that's really weird, right? And that's scary. And that's what I call code path disruption. And this happens because if I encounter an error and an exception is thrown, there's kind of this implicit, it's not explicit, that's the problem, there's an implicit change of execution path. And that's scary, right? Because that's the challenge. So this is a kind of long quote, but I think it's important, so I'm going to take the time to read it here. Tom Cargill says, counterintuitively, the hard part of coding exceptions is not the explicit throws and catches, The really hard part of using exceptions is to write all the intervening code in such a way that an arbitrary exception can propagate from its throw site to its handler, arriving safely and without damaging other parts of the program along the way. So you remember the nice little chart I had where down at the bottom was the implementation layer, and up at the top was the app logic. And what he's saying is, it's not hard to write the implementation. You just, oh, this problem, throw. And it's not really that hard to write the app logic. I mean, oh, an exception happens, I'm going to put up an alert, or I'm going to write something to a file. That's easy. The problem is all those layers of code. Because somebody has written their code with this expectation that we just do line of code, and then all of a sudden that's being disrupted. And that's the problem. So, so it sounds like this is really a problem for exception handling, but actually, this is really a problem for any kind of error handling. What Dave Abraham says is, exceptions are not hard. Error handling is hard. Exceptions makes error handling easier. When you're using return codes, you don't see this, code disruption thing, the path disruption, so you think it's easy. But the truth is, being consistent and disciplined and regular about always returning error codes and knowing how to handle them properly every time you detect a return code, that's hard. That's the hard part. So exceptions, they actually make it easier. There's a different hardness, there's a different challenge to it than using return codes, but it's actually easier because the return code challenge is to relentlessly follow a discipline that you have to go out of your way to do. So Tom Coggle wrote this article called Exception Handling, a False Sense of Security. And what he did was he analyzed, poor guy, there was a guy who had written an example. He said, this is how you write a template. This was in the early days of C++. He said, this is how you write a template. And he wrote a simple stat class using a template. And he also, by the way, he used exceptions for his error handling stuff. And Tom just kind of shredded it. First of all, he pointed out problems that had nothing to do with exceptions, just some bad coding, some things the guy had done. But then he started pointing out some exception safety problems that obviously nobody quite thought of. And that's why he titled his article, A False Sense of Security, saying you think you're handling all your situations because you're using exceptions. If you're not using exceptions properly, you've actually introduced other problems. And he even went so far, at the end of his article, he says, now this is the place in the article where I fix all the problems and I show you how to do stuff right. He said, I'm not actually sure how to do that. I'm going to let you guys think about that because I don't know how to solve the problem. He didn't make it. He did make it a challenge. He said, we need to solve this problem, but he didn't make it a teaser. He didn't say, later I'll tell you the answer. He said, I don't know. So here was what he didn't know. Here was the problem. So this is, as I said, a templated stat class. And he's calling pop. So what are we going to do? Well, you kind of have to know a little bit about the implementation here, but he's checking to say, okay, if top is less than 0, then we have an empty stack and we're trying to pop it. Otherwise, we return, it's implemented using this array at v, and we will return it and decrement, so we've popped an object, right? So what's the problem here? Why is this a problem that Tom said he couldn't solve? What's the issue? What's that? Okay. Where are we copying something? Right. We're returning up here. T is being returned, and that's by value, so it's being copied. So that could throw. So what? Why is that a problem? Right. Because we've decremented where we are, right? So in other words, we lost that object. We tried to make a copy of it, and then we decremented so we can no longer get to it, and the copy failed. Right? So Tom didn't know how to solve this. He said, I don't know how to solve this problem. But there's a stack class in the STL, right? Standard Template Library has a stack class, right? Right? They must have solved the problem somehow. What's the solution? Okay, pop and top. Okay, so the solution is that we actually have two separate functions. One is called pop, and what pop does is it takes the thing off the top, but it doesn't return it to you. It doesn't do the copy. So how do you get the top value? Well, then you call a function called top, and it doesn't pop. What it does is it returns the top. And so you've broken the problem into two parts where you can do a pop, and if that fails because the copy constructor throws, then you haven't actually, did I say it right? You do the top. You call top first to get that value. If you can't get the value, then you haven't yet popped. And only after you do get the value, then you call pop and pop it. Right? So he set out the challenge, and we rose to it. We figured it out. We know how to we write the STL so that it can handle this. And here's how we do it. Just exactly what you said. Yeah? But Cargill's article did, in fact, get a lot of attention. It kind of spread fear, uncertainty, and doubt. Some people said, well, it proves that exceptions aren't safe. And some people said, well, it proves that exceptions and templates used together aren't safe. But it's not exactly what he said. He didn't say exceptions are unsafe. He didn't even say exceptions were hard to use or too hard to use. He said they were challenging, but he didn't say they were too hard to use. What he said was we don't have all the answers, right? He's saying we don't know how to be exception safe. But that was back in 1994, right? So Dave Abrahams took it as his challenge. When he joins the standards committee, he said, I'm going to make certain that the standard library is exception safe. That's what I want to do. And that's what he did. And one of the things he did was what you saw there. He solved the problem with in the STL to make sure it was exception safe. And as I said before, I kind of got ahead of myself a little. I said, exception handling isn't hard. Error handling is hard. Exception handling makes it easier. So how many of you have heard of Joel on software? All right. I have to say I don't actually read his stuff regularly. I read it, when I see it, I read it kind of regularly. But I was looking at this blog entry that he had written back in 2005. And it was actually called Making Wrong Code Look Wrong. And his point was that if we could write code in such a way that it was easier to spot bugs, then we would spot them and fix them. That was his premise. And it's kind of a long thing. So I'm scrolling through it. And as I scroll down, there was a little snippet of code. And my eyes, of course, immediately look at the code because what can I say? I'm like you guys. I'm an engineer, right? You read the code first, and then you read the comments. Anyway, so I didn't even know what he was talking about. But there was this little snippet of code. It looked like that. 2 lines. I looked at that immediately, and I said, well, that's wrong code. And of course, then when I started reading, I realized that Joel agreed with me that it's wrong code, but unlike him, he looked at that and he said it didn't look wrong. But when I look at it, it looks wrong. And when you guys are finished with these 3 sessions, it's going to look wrong to you too, and we'll talk about why that is. But the reason he said that it's wrong is because he said, look, here's this code that you're going to do something and you're going to clean up. It's logical, straightforward, anybody can figure that out. But the problem is, in order for this to actually be safe code, you have to make certain that do something doesn't throw. Well, that's not that big a deal. You look at the source for do something. But of course, the challenge is that you also have to make sure that do something doesn't call anything that throws. Now it suddenly got to be a bigger problem. But you're not finished there yet. You also have to know that do something will never ever be modified to throw in the future. And that turns out to be a really hard problem, right? So that's why Joel said exceptions are extremely dangerous. If you write code like this, even if it looks like it works, even if you test it, it's possible you're not testing every code path. And even if you did test every code path, it's not possible for you to test every code path that will happen after some maintenance engineer makes a modification to it. Usually the maintenance engineer is you, and there's nobody stupider than a maintenance engineer, right? So those kinds of things happen, right? But as I said, when I looked at that, that's what I said. I said the code is wrong. That code is wrong. And when we're finished today, when you see code like that, you'll immediately say that code is wrong. So let's talk about some first steps. And as I say, I've been thinking about exceptions for a very, very long time. But if you had talked to me many years ago and said, how do we do this? Well, what I would have said is, look, you need to think carefully about what your return values are and what your error codes are and how you're going to correct all the problems when one of these things happens. You need to identify all the functions that can throw, including the things that call might throw, and you need to think about, separate these out. These are the ones that might throw. These are the ones that are safe, and then you think about what to do when they fail. And then I would say that the language actually has exception specifications in it that can help us, let the compiler help us figure these things out. And then I would say we can use try catch blocks to control flow of our program, right? That is not the way to do it. My initial thought about how to do this was all completely wrong. No question about it. That's the hard way. In fact, I'll go further. That's the wrong way, right? Don't do these things. As Yoda would say, you must unlearn what you have learned, and that's the challenge, right? So I heard some of you guys typing stuff in and all this. No, you don't want to do any of those. Here's the right way. We're going to think structurally. We're going to maintain invariants. When we think structurally, maintain invariants, as long as we maintain the invariants, then we're going to be always in a state where if an exception is encountered, even if we have code path disruption, the invariants are maintained, and we're writing safe code. So how do we do that? Well, you've come to the right place. I'm going to give you a set of guidelines. They are few enough to fit on one slide. Some of them are hard requirements that basically anybody trying to write exception-safe code has got to follow those. Some of them are just what I call really sound advice, where if you want to write exception code, you really, really should follow them. But that's what it's going to be, a set of guidelines. But before we get to there, we need to learn a little bit more backstory. And so we're going to look at the exception safety guarantees. And this was one of the things that Dave Abrahams came up with when he was working on the standard library and trying to define what exception safety means. So he came up with three categories of exception safety. First is the basic guarantee. And the basic guarantee says that even if an exception is thrown, our invariants are preserved, no resources are leaked. Notice it doesn't make any guarantees about the state of our system, except that invariants are not violated and resources are not leaked. In other words, it's possible to recover from this state. But it doesn't specify exactly what the state is. If you need that, then we talk about the strong guarantee. And this says if an exception is thrown, there are no effects. And then the last guarantee is the no throw, which is this operation will not emit an exception. Okay. So Yoda has a term for the strong guarantee. He says do or do not. What is it we call this? It either happens or it doesn't happen. What is that? A transaction. I knew there was somebody with some database skills in here, right? It's a transaction. This is the transactional approach. So let's talk about the basic guarantee. It turns out that there's probably code in all of our code bases. Maybe some of you work at an exceptional institution. But there's probably code that doesn't meet the basic guarantee. Well, why don't we talk about that kind of code? Well, it's for a very simple reason. Job zero of trying to write exceptional safe code is to deal with any function that doesn't meet the basic guarantee. If it doesn't meet the basic guarantee, you're already broke. You cannot build safe code on top of that. So in a sense, it's foolish to assume that all code at least meets the basic guarantee, because we know better, some code won't. But the problem is, if you're going to have a world in which some code doesn't meet the basic guarantee, you can't move forward. Job zero has to be, we got to fix everything so that it at least meets the basic guarantee. And we just can't talk about, if there's some piece of code that I might call, and as soon as I call it, I'm now in an invalid state, I just can't call that code. I mean, there's no way around that, right? The other thing is that we're also going to assume that unless we know otherwise, the code that we're looking at meets the basic guarantee and only the basic guarantee. So when I see function foo, I never have to say, although I will through the rest of the session, but I'll never have to say, by the way, foo might throw. Because if we haven't explicitly said that foo doesn't throw, or we haven't explicitly said that when foo throws that the strong guarantee is held, then we have to assume otherwise. Because the assumption we're going to make on any code that we know anything about is that it meets the base guarantee. And again, not because we're so foolish and naive to think that all code does, but because if it doesn't, we can't go any further. There's no point in talking about how you might call foo if calling foo could put you in a bad state. So you have to avoid that. So that's why we say this. And it turns out that the vast majority of code, nobody has ever explicitly said, by the way, this is the strong guarantee or this is the no-throw guarantee. Some code is like that. Some people say, this won't throw. But most code doesn't have any guarantees at all. So the vast majority of code we assume throws. And that may be scary. It was scary to me when I first started thinking, how can we control all this nasty throwing code, right? But it turns out we're okay with this. Once we get through this, we're going to be really okay with this. Okay, so now we're going to look at something that's C++ 11 specific. And so we introduced move operations in C++ 11. But the rest of this is C++ 03. And that is, here's where our no-throw is required. Anytime we want to clean something up, right? If we're in the cleanup operation, that has to not throw. And this actually does represent a problem, because there are times when we might say something like, oh, cleaning up involves flushing this buffer, part of my cleanup, and it's possible that flushing the buffer fails, and so I might want to throw. But no, we cannot design that. It absolutely is a requirement that our assumption that if we're going to write exception-safe code, then cleanup code can't fail. So we either have to just log that sort of thing, or else we have to make absolutely certain that we do all our buffer flushing before cleanup happens. Those are our options. And then swap. Now swap might not seem very important to you, but we'll find out later swap is really cool. Is Walter in here? Oh, it's too bad. Oh no, Walter's giving a session at the same time. He told me he wanted to be here, but he couldn't. So when we talk about, we'll get more into this, but move operations, it isn't technically necessary in the language that every move operation not throw. But if you're going to write exception-safe code, you need to make certain that your moves don't throw, which is somewhat about what Brianna was saying. It would just be easier if you could just make the statement that anything that moves doesn't throw, otherwise, but we didn't quite make that statement. But from a practical point of view, we need to be there. We really need to be there. So let's look from the caller's point of view, which is the no-throw requirements are the only functions that we need to be stronger than basic. So we have some functions that we just outlined, the cleanup functions. They'll have to be no-throw. But actually, to write exception-safe code, it's never really necessary that we have the strong guarantee. And we will assume, as I said before, all code meets the basic guarantee and no stronger unless something, some comment or something else explicitly tells us that we know that this code is either meeting the strong guarantee or else meeting the no-throw guarantee. We're actually okay with this. We're going to be able to write code where almost everything is just the basic guarantee. Now, from the implementer's point of view, obviously, it's absolutely critical that all the code we write meets the basic guarantee. If you're writing a function and you know, well, by the way, this might throw, and if it does throw, I'm going to leak this buffer, you just can't write that code, right? I mean, that's just, you can't be safe if you write that code. So you've got to fix that. And then for those situations where the no-throw is required, such as cleanup code, destructors, things like that, where we need the no-throw, and swap and moves, as we talked about, we need to do no-throw. And then the other thing is that in situations where we have the strong guarantee, you should document that. And the important thing is that you really only want to provide the strong guarantee where it's natural, and we'll talk about what that means. But Dave actually has told me he's a little bit questioned about his use of terminology. He's afraid that people strive for the strong guarantees. Like, can I write my code so that it delivers a strong guarantee? And what he says is that may actually be a pessimization. You may be slowing your code down in order to get the strong guarantee in situations where it's not really important. Right? So users want to be able to call your code and have it be performant. If they need the strong guarantee, that's a different issue. But don't assume they do need it. In fact, the challenge he made to me, he said, John, when have you ever been in a situation where you needed it? It's like, oh, well, I'm sure there was some time. So let's talk about this. Here is a snippet of vector, right? And the vector is telling us that the standard library tells us that this is going to meet the strong guarantee when you do a pushback. So let's talk about what happens when you do a pushback. There's two cases in pushback, right? What are the two cases? From the implementation side of view, if I'm going to do a pushback on vector, what are the two cases? There's either room or there's not room, or as you said, right. So let's talk about the situation first where there's room, where our size is less than our capacity. So what are we doing here? This weird new. We showed you some weird new before. What is this? Placement new, where you're basically saying, I'm going to create T, and it's going to be a copy constructor because I'm going to copy that T. But I'm going to take a T in this place, and where this place is somewhere, you don't know exactly what size is. We assume size is the offset into the buffer of our vector, right? So we're making a new thingy, right? Now, what would happen, and then once we've made it, we move size. We increase size because we got a new guy, right? Now, where might we see throwing happen? Can this throw? No. That size is an integer. I mean, we don't have the whole code, but we assume size is an integer of some kind. Otherwise, this is a really weird vector. Could this throw? Okay. How do we know? Because we're not told otherwise. That's how we know, right? Basic guarantee only. So it may throw. If this throws, then are we going to get the object created in the buffer? No, it's not going to be there. Does that leave us in a bad state? Are our invariants violated? Why not? Some people are shaking their head. Nobody actually says anything. Because nothing's happened, right? We haven't touched any of the members of vector. Where do we touch the members of vector? Down here, where we never get to if this throws. So is this exception safe? Does it meet the basic guarantee? Yes. Does it meet the strong guarantee? Right. It's the same vector with the same data in it. Everything is the same if this threw. Right? So it meets the strong guarantee. How much extra performance, how much extra work did we have to do? I don't mean mental work, but I mean how much work are we having our code do in order to give you the strong guarantee? None. Because even if we'd written it stupidly and said something like, well, let's increment size first and then do the buffer at size -1 or something like that. Even if we'd done it stupidly, it wouldn't have been any faster. In fact, that way would probably have been slower, right? So let's talk about the other situation. And that is where we're out of room. Our size is equal to our capacity. And so, wow, this is more complicated now. What are we going to do? Well, we need, let me look at the code here a little bit. Think about this a second. What are we doing here? Oh, pushback. Okay, so the first line is down here, right? We are going to create a new object in, I just see we're talking. That's why it doesn't make sense. We're going to allocate a new buffer. We're going to copy all the existing items in the new buffer, and we're going to set the new capacity, right? Once we do that, then we can delete this temporary buffer and change our size. So we swap the buffers and do this. Notice that this part up here could easily throw. But again, allocating the new buffer can throw. Copying the existing items in the new buffer can throw. But we haven't changed any of our data members until we get to this step, which is set the new capacity, right? So again, this is the way you would implement it, and no extra work is being done to give you the strong guarantee. This is what Dave means when he says you want to give the strong guarantee when it's natural. It didn't cost us anything. Now, so the only two things you need to be aware of is the strong guarantee is identifying where it's natural and making sure you provide it, and one other thing. Strong guarantee. Document it. Because as I said before, unless you actually say it's the strong guarantee, we're going to assume it's not. Okay. So for many functions, the strong guarantee comes free. And in situations where it doesn't, we generally don't want to provide it. Let's think about an example where, yes?
So you said in the previous slide, it satisfies the strong warranty.
Yes. Let's talk about that. Let's make. I'm sorry, say that again?
You can leave the temporary part.
It will leak it. This is not a good example of a code, because the way we should do this is we should probably put this into some kind of RAI holder. So this code is not good. If we did that, it would be no more performant, and no less performant. So yes, this is not a good example, and I should use unique pointer or something here, right? Because you were absolutely right. That in this code written this way, that's a bug, right? The point is, though, that written this way with putting this in unique pointer, there's no performance penalty. It's written as performantly as it could, strong enough. Yeah, Lisa. Put it in a vector. That would work. And the vector even has strong guarantee for us. So yeah, there's no problem. Okay. For many functions, if you get the basic guarantee, the strong guarantee is free. And what these things tend to have in common is you're dealing with one resource at a time. Right? So let's talk about the situation where this wouldn't be. Imagine that I wanted to do vector insert. So what is a vector? Vector is an allocated array. I want to insert an object. Thank you. I want to insert an object right in the middle of the vector. The standard does not give us the strong guarantee for this operation. Give us the basic guarantee. Could we imagine an implementation where insert is the strong guarantee? Well, first of all, what's the challenge? Why is it hard to make it the strong guarantee? Why doesn't that just come natural? What's the problem? That's right. If you're doing an insert, what are you going to have to do? You're going to move everything down and then put something new, right? So if we're not 11 yet and we're not doing moves, then you're going to do it by copying. The copy could throw, and if that happens, we're in a state where we've made modifications. We can't roll them back because the rolling back may also throw. So we're kind of, we just can't give you the strong guarantee. But let's say I absolutely must have strong guarantee for insert. Can we implement that? Is there a way to do it? How would we do this? How would you? What? Rotate? That's not going to throw? Well, but again, as long as you have non-throwing moves, you can do that. Right. What's that? Exactly. That's the way we can do it. We just have to copy the entire buffer, do the insert on the copy. Once we're certain that it's going to work, then we do a swap. Would that be exception safe? Would it be the strong guarantee? Would it be what our users want us to do? When I call insert on a buffer, it's expensive enough that you're going to copy half the buffer down to make room for it. Do I really want you to copy the other, the entire buffer first and then copy half the stuff down to make room for it? No. Actually, it could be implemented a little more efficiently than that, I guess. But the point is, there's 2 points here. One is we don't want vector to be implemented that way because it's a performance penalty that we don't want always. Maybe sometimes we do want it, but notice that when we do want it, we can do that ourselves. Right? It's just as easy for us to just make a copy of the vector, make the operation we want, and if it succeeds, we do a swap on the vector. It's maybe a little bit more overhead, but a trivial amount of overhead. We can do that ourselves. It's not necessary for the low-level implementation to do that for us. So the key point I'm trying to make here is that the strong guarantee is not a goal. There are some times, generally speaking, when you're dealing with a single resource, that very often it's easy and cheap and you give the strong guarantee without even thinking about it. But many times, the strong guarantee would be a performance cost that your users don't want, and in that situation, don't do it. So this is the example I was about to give you here. All right, so we're now going to dive into some mechanisms. How are we doing on time here? 10 minutes here. Let's get started on this. As I said, I really need to keep going. I don't really want to even break for questions, but if you have a question, please.
And I will say some of this, you're all going to think, oh, I've been using exceptions. I understand the mechanics. I know how it's, this is the part that Cargill said is easy. We throw at the bottom and we catch at the top, and that's all easy, right? Okay, my challenge to you is that I suspect you're going to learn something, because I certainly learned a few things in researching it, right? So even though you're old hands at C++, you might learn one or two things. So let's do that. The first thing we want to talk about is error detection. And we're not actually going to talk about error detection at all. What we're going to do is talk about what you do when you detect an error, which is throw the exception, right? So here's what what our code might look like. Some runtime error is detected. We create some object and we throw the object. Okay, is the object thrown? I just said that, didn't I? Why am I asking such a stupid question? I just said the object is thrown. Is the object thrown? No. The standard very clearly says that a copy is thrown. Now, a compiler can elide this. A clever compiler could figure out, hey, look, he's making this object, and the only thing he's doing is throwing it, and I need to copy it, so I could just make it in the copied place and not actually do the copy. But that's an optimization that we can assume the compiler might do, but we can't assume the compiler will do. So the rule is anything you might want to throw has to be copyable, because it's going to actually be copied. Can we throw a pointer? Pointer is just a value that could be copied. We can throw a pointer. Can we throw a reference? Well, that's kind of weird, huh? Actually, syntactically, there's just no way to throw a reference, because if you throw a reference, it's going to say, well, that's a reference to this object. I'm going to throw the object. I'm going to copy the object, right? So no, the answer is you can't throw a reference. But here's the problem. Is it a good idea to throw a pointer? You're laughing. Somebody thinks it's not a good idea, right? Why is it not a good idea? Well, think about who's going to catch it. You're going to catch a pointer, right? What are you going to do with it? Well, assume you're going to dereference it. You're going to try to do something interesting with a pointer. And then what are you going to do with it? You're either going to delete it or you're not. And when you call delete, you could call delete or you could call free, because who knows, right? And should you do that or not? Well, if this pointer was to some global object, then you would really be hosed. And if it's not to a global object, it's something that allocated and you don't delete it, then you're going to. So throwing a pointer is just a bad idea. It's not so much syntactical problem or even a technical problem, but semantically it's really weird that you're throwing pointers around. And we can't throw it around. All right. So this is kind of the more common way. I said that we could in fact instantiate an object and then throw it. But the way more common thing is to just say I'm going to throw, and then I actually make what I'm throwing as a temporary right there as part of my expression. Throw this thing. Now, let's talk about this S up here. It's a string. I tried to make it kind of long so it would defeat any local short string optimization we might have. So we've got this string that's on a stack, right? And then we throw this object. Now, what exactly is a string? It's an allocated array of characters, right? Short string optimization might cheat on this, but generally speaking, it's an allocated array of characters. And if you allocate something, what do we need to do? We need to release it at some point in some way. Is that going to happen if we throw? Ignoring the throw, where would this releasing of the resource be? Right here, right? But we're never going to get right here, are we? Why not? Because we're going to throw. So does that mean that we're going to leak the bytes that were allocated by the string class? So far? Well, the language says that would be a bad thing. So the language specifies that what Lisa said is correct. I said that we release it when we get here. And that's the good, easy way to think about it. But the truth is, what the language actually says, it's when we leave this scope. And when we throw, we leave the scope. So however you want to conceive of it, you can say that a throw magically shortcuts to here, or you can say whatever. But the point is that the language will make certain that all local objects have their destructors properly called whenever we throw an exception from a function. And that actually works at the higher level too. If you call a function that throws, even if you're not throwing that function, then that's going to get cleaned up. So let's talk a little bit about handling the cache. How are we doing on time now? We still got some time. Let's keep going a little bit. Unless you may have questions? We okay? All right. Yeah. That would be a bad thing. We're going to talk a little bit about that. Later. In fact, kind of coming right up, we're going to talk a little bit about this.
Can you repeat the question?
Oh, I'm sorry. He said, what would happen if, remember, when we throw something, it makes a copy. He says, what happens if the copy constructor in that copy, what if that throws something, right? And the answer is really bad. So bad I didn't even want to answer the question. So we'll talk about this. All right, so let's talk about catching. So here we have this, here's syntactically what it is there's a try, and then these braces, and then the catch, and then it's specifying something that could be catched, and then there's this ... thing, and so this is what we have. Interestingly enough, or at least I found it interesting, maybe you guys will think it's kind of crazy, one of the things that Bjarne has pointed out is that try does nothing. Try is completely useless. It does nothing. The compiler is smart enough that if you were to say, oh, by the way, here's a right bracket, a right brace, followed immediately by a catch, then the compiler knows where that brace started and it could say, oh, well, here's an area that we might throw an exception from. So why is there a try there? Who can tell me? Yes, Lisa. People like keywords. That was basically it. What Bjarne said is every time he tried to explain this to people, they got confused without the try. It just didn't make sense to the people. The compiler was fine with it. But, people, well, what can you say? Okay. So the key thing here is that this catch, what we're saying is catch, capital A, I tried to make it look like that's a type, and then A is an object of a type. It looks like a function argument, right? This is reminiscent of a function. This is how, when you write a function, what do you write? You write the type, and you write the name you're going to give to that type. And in fact, it is kind of like that in that inside here is code that can use A, right? Because it's as if it's been passed to a function, right? And then down here, we have this catch ... It's sometimes called catch-all. And what it says is this is a generic handling code. It can't use A because A is up in this other scope. In fact, it can't refer to the function, to the exception at all. Does that mean the exception is lost to us? No. Lisa has a way of recovering it. We'll talk about that later. So let's talk dig a little bit more deeply here. As we said, this is like a function argument. And what does this mean if this were a function argument? If I actually had a function called catch, which don't even try that. But what does this mean? What's that? Well, okay, it's a new scope, and in that scope, little a is going to be defined in the scope. Right. It's also saying that a has been created for this scope, right? This is a value. If it was a function parameter, we would say it's taken by value, which means this copy is happening. Again, either might have lied that, but we'll assume that a copy is happening because that's what might happen. And when we copy by value, what happens? Well, one of the things that we have to think about when we copy by value is slicing. What does slicing mean? Exactly. Again, having nothing whatsoever to do with exceptions, if I call a function and the function takes A and I call it with an object that is actually derived from A, what's going to happen? Well, it's actually going to copy the part that's the A part of a larger object. You're not going to have a nice day, right? So this may not be a great thing there. And the other thing is that because we're copying, again, that copy might throw. Okay. If we were to catch by reference, on the other hand, then it's actually possible that when we say that I want to modify the object and then say throw, and when I say throw without a parameter, that's a rethrow. It means throw the object that has been that is the exception that I'm catching. Rethrow that, as if this little thing was just a pass through, right? But that pass-through did a modification. So if I tried to do something like that with catch by value, I could mutate the A. It's my A. I can do anything I want with it. But if I said rethrow, I'm throwing the original, not my copy. So my modifications are all lost. Right? In this case, I modify before throwing. So that takes the value situation. That takes catching by reference. What about catching by pointer? You will never catch by pointer. Why do you not catch by pointer? Because you don't throw by pointer, right? We talked about that earlier, right? So we always want to catch by reference. This is the reason. So how are we doing? We're there. You guys take a break, right? And then come back. Yeah, have fun.